approach to centrifugal performance. And for those of you who wanted to come and have a engaging discussion about compressor performance and get into crazy, details, we'll have to have another class for you. This is going to be mostly a lecture, which is the boringest way to do it. But I have a lot of pictures and I don't mind questions. Online, I have my volume up, so hopefully I hear you if you say something. Um, I don't think the screens that everyone's watching will see you raise your hand, so I don't know. Send up a smoke signal if you have a question and you want to stop. I really am okay with any interruptions, especially if I'm off topic or you need me to move on. Um, I finished this presentation at 1 o'clock last night, and I will give you a warning. It's not finished. What I want to do with this goes beyond what we'll get done today. And we're gonna fill 2 hours, I would think, easily. Um, but it's going to be a lot of me rambling. And I think that's a good introduction. So as I was kind of mentioning, as we waited for people to roll in, Chrissy said, let's talk about performance. There's a difference between performance and aero to me. Super smart people that know, um, equations and all that, college stuff. They're the scientists, they do aero, like a Jay Cook, right? John, you probably are an aero person, but okay. I am not an arrow person. I love arrow. I love arrow people, but I'm not an arrow person because every time they tell me the difference between isentropic and polytropic, my eyes crossed, and I still can't tell. I can go to the thing and I can calculate the difference. I really don't get it. Okay, when I see an enthalpy chart, I that's why I don't do steam turbines because they're all about enthalpy. Okay. Um, I started doing this in 1991 as a high schooler. My very first session was like getting a database of impellers for a guy named Jim Sorokas. Okay. Um, I worked with Karen Travaskis in the Aero group, and I still have Christy Schwartz's 3-ring binders of everything you need to know about Aero. I have them in a closet and I haven't opened them in 12 years, but I've been through it all. Okay. I haven't sat through many test stand issues, but I know everybody that has, and they helped me do my job for a lot of years, right? So then I started looking around and I go, oh my gosh, they're pretty much all gone, and I'm the only one left. I must not know how to get a job or something. But I like my job, and my job is basically inside the compressor. Okay, so I put in my background as I'm a scent perf user, and most of you, if you're new, you don't know what scent perf is, but I'm the only one that here that's ran scent perf that I know of. And I can still look up a scent perf file. So if you have a compressor that's 40, 50 years old and you need to model it, you may need me to go get those. And I used to do it pretty regularly. And that's how I know there's more new people than ever because no one even asked for it, right? We have better techniques today for doing those things. And for let's say applied technology approach where you don't really know what the compressor is, you don't know what the designers built the individual components, you don't know what went into it, but you have an output curve. We have really good techniques for backing into the performance of a compressor and then determining if it can run it and set a new set of conditions. So maybe people just don't need the scent perf. They don't need that old input the way they used to. But I'm a scent perf guy. I'm really a smart perf guy because boy, I was in the job when they made that. I was in the very initial meetings when they decided to make Bubble R, if you know what Bubble R is, but that's when it used to be a new equipment tool, and they said, well, we got to get these aftermarket guys using this tool, right? So we made Bubble R, and then later we went Scent Perf or Client Perf. So when Smart Perf was really doing well, customers wanted to do it. We used to take it on our laptop offline, right? We download the software we needed and the compressor we needed. We go to the customer site and we do performance right in front of them. Hey, what if the temperature went up 5 degrees? Well, let me show you, right? And we could make online selections and hone in on the final selection. They would buy it and you'd bring it back and download it and say, okay, build this, guys. We actually have done that a few times. And then that got out of popularity, I guess, because there was security and all these other things. And Citrix came and they were like, oh, we got to do everything online. And so they took that away from us. There was too many things to juggle. Well, about that time is when we made Client Perf, which was the customers could log into Citrix and run their own performance. So we would set up a file, lock it in place, publish it to them, and they would log in to Citrix into SmartPerf and only see their one file. But that way they could run conditions and it would save tech support, the 10 hours and the billing and all that stuff. We used to make $5,000 a pop to make a new set of curves for a customer. So we charge them 10,000, set them up on SmartPerf, and then they would proceed to never use that again. So client perf went away. Now we're into ChessGUI, and ChessGUI DCD, which is the datum input to ChessGUI. We're doing it, Peyton, right? I mean, we're going to do more of it. There's the RS7s, the RS6s that we're going to take over some of the stuff, but they're a little bit too big to fit in. But we're getting there. What's upcoming in Duisburg, they're still doing a lot of development, and I take these opportunities to spread this. It's good work. It's good news. We don't often hear it, but they're developing a new line. Tomorrow's lineup is going to be called the RSFX for, I don't know, future express awesomeness. I don't know, but it's going to be the most compact, highest head, best efficiency. So it's going to replace, if you're a datum person or Cooper person, whatever your lineup is, but for us, it's datum lineup. It's going to replace the 275, the low flow coefficient wheels, and upwards of the 466 if they can stretch their knowledge-based, designs into that. So that's one slide. We're going to have to go faster. We will. Okay, what we're not going to do, if you didn't pick that up, we're not going to do any of that. If you need to talk about Euler's equation or Bernoulli's equation, now maybe Bueller, I could talk about Bueller, but that's a movie reference. Okay, and performance, we got to say what we're doing. It's centrifugal performance. We're not going to talk about recips. We're not talking about screw compressors or any of that. We're just going to talk about this. And so that's the smallest compressor, and it's not the biggest compressor. That's just really big for Dresser Clark, right? IRs had some 128. They built a 140-inch case ID. Okay, and I didn't get the one where they had the GMC Jimmy inside the compressor case. That's just a 9B. So yes, that, if you can't tell, you could literally drive a car into that compressor there, the compressor casing. That picture's out there as well. By the way, I just mentioned, since I say new people, I am an old person. My dad was working here, and he's the one that, when they went into production meeting, they wanted to play a joke on I think it was Jim Beeson's car, but they went and took his car keys and they actually drove the guy's car into that compressor without his knowledge. And he came out of his production meeting, and the whole meeting just walked behind him, and he's like, "Why is everybody following me?" And he's like, "Why is my car in the compressor over there?" So, anyways, I've been alive for a long time, even though I may look younger. Okay. What are we also not going to talk about today? Customers talk about all the things on the outside of this bubble, obsolescence, reliability, all that stuff, right? But we sell compressors to them and we have to solve their problems. So I'm remiss not to mention that compressors do those things for the customer. They don't really talk about the insides too much unless they're having a problem with it, right? So we're the bubble. We talk about, like, for revamp perspective, we talk about upgrades. That's anything mechanical on the compressor, right? Bearing seals, you know that. But the rest of that bubble that I live in, the revamp land, is head capacity and efficiency, and that is performance. So 3/4 of the bubble is performance in my mind. In reality, that's a very small sliver. There's more mechanical stuff that goes on with a compressor than performance, right? But without the performance, you don't need a compressor. So that's how it looks in my brain. Very simplistic bubble. The other basics of performance is, you got to remember this. It's super simple, guys. 5 inputs, 2 outputs, or any of those outputs, power and speed, can become an input. But you got 7 things you're doing. Capacity is this middle thing, flow. The head and efficiency is all baked into this. Pressure, suction temperature, mole weight. There's a discharge temperature in there. You could say that's an output, but these are the inputs, and that's typically the output, pressure and speed. Okay, this is what it looks like. Now, the focus of this presentation is either going to be talking about the components in the compressor that make performance, or talking about how we speak about performance to a customer. Sometimes they'll say, "Well, how much head are you making?" Nobody's going to say that. They're going to say, "I need to go from this pressure to that pressure," right? No one's going to say, there's going to be a few people say, "Well, I need to make 50,000 feet ahead." They're rare, okay? But this is the way that you talk about compressor performance. And on the right-hand side of this screen is the head equation if you're a piece of gas and you need to get from one place to the next. And that's how the customer's going to say it. I need to get this gas to that place that's pressure 2 versus pressure 1. And I got this gas that's baked in the R equation, right? That's your mole weight. And it's sitting there at whatever temperature. And baked into this is some efficiency components and other high fluid stuff. I told you, we're not going to do the math. That's the equation. There it is. On the left side of the screen is a really easy one. That's the compressor side of the head equation. Mu, which is the head coefficient, U squared, which is the tip speed of the compressor, and G, which is the gravitational constant. That's it. But you say, well, what's the head coefficient? Well, that's a very complicated thing to go and calculate, okay? But each compressor has a mu value, a head coefficient. Inside the compressor is multiple stages. Each one of those stages has a mu value. Okay, so I'm not gonna peel into this a lot, but I want you to have that impression that this curve could represent a stage, it could represent a section of compression, or it could represent multiple sections of compression. There is no title on that curve, so you don't know what it's showing you. Okay, there's also two curves there that you're not seeing double. It's early, no one's drinking. There's a black one and a blue one. I come from revamp land. If you see these, I always have to compare compressors from the original to the revamp. So this is just an example I grabbed, okay? The other key thing to this is that it's capacity and head. Okay, so on the bottom here, we're showing this on volume flow, and on the y-axis is polytropic head. If you display a compressor, centrifugal compressor, in terms of volumetric flow and polytropic head, you can do it on one graph. Within limits, you can change temperature, pressure, and mole weight, and you get the same graph. Within limits. I got some other graphs. We'll see how that varies. And you can plot them over top of each other, and it gets a little fuzzy. If there's massive changes, and I don't have this in here, there's a curve that tells you how long that will stay accurate for. I didn't put that in this presentation. That's why I said the presentation is not done. It'll probably get in there eventually. Okay. So what is compression? I was going to get that little picture off the internet where everybody compresses the cans, right? Where they heat the can up, they put hot water in it, and they have a bowl of cold water, and then they turn the hot can over into the cold water, and then it crumples. Okay, you just saw it in your mind. But that's what's going on here is that you take gas from one pressure and temperature and energy state, and you take it to a higher level of pressure and energy, okay? And you compress it. So we're going to visualize that a couple different ways. So head, specific energy required to compress a given volume of gas from one energy state to another. Capacity is how fast you're going to do it, okay? This is a representation of a whole bunch of compressors. And what do we look at? We look at pressure rating, right? Because if you need to go to 5,000 pounds, you better not have a compressor that only goes to 1,000 because it'll explode, right? The capacity, because that's really important. There's a range of sizes of the impellers. There's a range of the size of the capacity. And if you have a huge compressor and you try to run no flow through it, centrifugal compressors will do what we call surge. That's a bad thing. And that's not in this presentation. Someday, maybe I'll add it. Does anybody know what surge is? When you want the gas to go one way, but it goes the other way, right? Makes a lot of noise, can make a lot of noise. It could be silent. It can be very damaging or could not be. Depends on the energy level that's in there. But I'm going to tell you, when I started, when I was a new person, they sent you out to the test stand. We don't have a test stand anymore. It was very, very memorable experience. First, if you were a new person, they give you a dry bulb and they say, hey, we need this reading. And they make you go up on top of the compressor and turn that. That's just to measure that you are actually a new person and that you don't know that they have instrumentation to do that. You don't need that. But I've done it, and it's fun. The other thing that they do typically when you're new is when they're running a compressor, they will go into audible surge with a customer's compressor. It's probably not recommended, but they just want to see just how far you can jump. So if you're standing right next to the compressor and they go into surge event, everything shakes. You think you're in an earthquake. You think there's a jet going by you at Mach 1. It's crazy, right? There's just noise everywhere and energy everywhere. That's a surge event. So if you don't get a chance to stand near a compressor in your career, look for it. Just honestly, it's worth the road trip. Take a tour of a facility and go stand next to a compressor that's running, not one that's surging. Okay, this is what a compressor looks like in case we thought we were in the wrong class. So the little arrows tell you where the gas is going. Okay. It goes in the inlet. That's the blue arrow. And it comes out the discharge. That's the red arrow. So this, what we're going to talk about when we're talking about performance is three things. This is it. This is the whole class. We can stop after this slide. The gas has to get in. You have to do some work on it. You have to compress it. And then it has to get out. If you forget to get it in or you forget to get it out, you fail. Okay. And our biggest problems in the last few years is when people forget these things. Okay. Hillcorp, we decided to make one of them output things more like a valve, and they close the valve and then your gas can't get out. We did some amazing compression inside that compressor, but it was terrible on the test stand. So don't forget the ins and the outs. These two holes are the most important holes on the compressor. I don't care. Rotodynamicists and mechanical guys are going to tell you that oil holes are important and vent holes are important and all that other stuff. I don't care. These two are the most important. Without the in hole and the out hole, you don't have a compressor. Okay. And impellers are important too. So let's take a look at what they look like. These things are called impellers. And I say these things, they're the ones here on, this is a shaft, right? We all know that. And we're not gonna bear down to those levels of things. We're gonna stay on the flow path. But the impellers are the prime mover of the gas, right? So there's the coupling imparts torque to the shaft imparts torque to the impellers, they spin. They spin at a very high rate. Let's say 30,000 is the highest I've dealt with. And the slowest is maybe around 800 RPM. So the bigger it is, the slower it'll spin. Why? Because the tip speed of that's the speed at which the OD of the impeller is spinning kind of generates the work. Okay. So if you have a really, really big impeller, let's say a 75-inch impeller, it's going to turn way slower than if you have a 15-inch impeller. Okay. Um, the smallest impeller I've ever dealt with quoting was about 6 inches, and we never built it. Okay. There are micro compressors and there are applications for them, but that's really that's like a tiny amount of flow. So a lot of people, when they're in that range, they'll go to a recip or do some other things. Or go down to Home Depot and buy some air compressors, right? But you can see here, you get the impression that the temperature is raising. You get the impression that the volume is reducing. So we're going to talk about volume reduction a little bit. And that's what it looks like. This was a Jim Soroka slide, and there's like a series of fans. And he says, well, each one of those fans, think of it as an impeller. I mean, it is. It's just an axial impeller, right? They usually call it fan blades. There's blades on the impeller. Okay. This is another view of it. This is when the gas goes through. This comes out of the compressor basics spreadsheets and presentations. You'll see a lot of that in here. I just want you to have a few slides that let you visualize the flow. Okay. And if you're visualizing this flow, you got to understand this is completely and utterly wrong in my envisionment, because when you start moving gas really fast, they don't all stack up here, right? You don't go from, I mean, this is trying to give you the impression that it's compressing and it's putting all the molecules closer together. I don't love this environment, but it's okay. We continue to use it. It'll fill your mind with a visualization. But I like this one better, even though this one's technically wrong as well. So let's say a gas particle is coming to an impeller. It's going to be coming straight at it. Not always, but let's just say in this picture. So that little portion of the impeller right here is where it's going to capture the gas. Oh, you can't see that. Is there a way I can put it? Look at that. I can if I turn around. Okay, excellent. So this little portion right here is where the eye of the impeller is and where the gas particle might go into it. Well, now I can't see it. So that gas is going right directly into the page. When it gets to the impeller, which is spinning, let's say, at 10,000 RPM, it's going to go around that probably once or twice. It's not going to go from here to there. It's going to go all the way in a circle, right? But it would eventually go up the pressure side of that blade and then exit the impeller. So this is This is a representation of what the gas particle is going to do, but it's going to move faster and faster as it goes. So when it gets to this point, there's a component of motion that is out away from the impeller, and there's a component of motion that's tangential with the impeller's rotation. Okay. If you can envision two vectors, they make a triangle. Okay. So we're not going to get into velocity triangles. That was on that first page right in the middle if you didn't notice it. We're not going to talk about velocity triangles, but I want you to have a visualization of that gas particle does not come off straight. Like this gives the impression that it comes off and it goes straight up, but it isn't. It's following those purple lines. Okay. I'm gonna turn around again. We're going to talk about stages. You have to have a visualization of what a stage is and what the boundary layer for that stage is. This is one of those things that talks about as it goes through the compressor. This is not a representation of a stage. This is several stages. And it doesn't even show where the end is. That gas that's leaving the second impeller there is leaving the compressor. It's probably going to a volute. Okay, so we're going to talk about all these components and what each one of those things is doing in the compressor. This is another picture of a stage. They represented this entire thing. The blue area, the inlet guide area, that's portion of the upstream stage. So that's not a stage. It's a stage and a quarter because it represented an inlet guide, then a stage, and it has the inlet guide of the downstage. So a stage, and here's a picture of it a little bit better. It goes from the leading edge of the impeller that you're talking about through the diffuser, the return bend, the return channel, and the inlet guide following the impeller, right up until the next impeller. Or if it's leaving the compressor through its volute, collector, flange, you name it. So a stage of compression is from the impeller through to the next impeller. I will give one caveat to that is that there is leakage. Whenever you have a rotating piece and a stationary piece, you're going to have a seal. There's a labby seal. It's really tiny on that picture, but over here on the right, you can see the little spiky things at the impeller eye cover. That is a seal, and there will be leakage through that. Whoops. So we're actually going to back up. If you could see on the diagram on the right, there's station numbers. 1 is at the impeller entrance, 2 is at the impeller exit, 3 is at the diffuser entrance, 4 is in the middle of the diffuser, B5 is up there at the top of the diffuser, B6 is at the end of the return bend or the returning section in the beginning of the return channel. B7 is at the end of the return channel. B8 is at the end of the inlet guide portion. There is a section mentally called 0. It's where we begin, and that's right before the flow comes in. So at the end of the inlet guide, right before the impeller starts, there's a 0 station. There's a 9 station, but 9 is equal to 0. So that's a stage of compression. If you represent a compressor, and we're going to show you a CIX curve, what we call CIX curve. I don't know, did Cooper have a name for the head coefficient and efficiency versus Q over N? Head coefficient, you just call the head coefficient curve or okay. It's a dimensionless curve. We have one of these in here. But we called it CX curve. I never knew what that stood for. But we called it that. It's a little short acronym for
Six was at the top of the tunnel.
station 6 was at the top. Okay.
7 was at the entry to the channels. So
Okay. So John was explaining that at the top of the return bend, they had a station. There was a 7 and 8, and a 9 was probably where our 8 was. And if you go to Duisburg, which that's a 4-letter word if anyone's counting those, if you go there, they have slightly different stations, but they do a really nice job. They have a spec that dictates every single one of these flow path components. So we're going to talk about each one of those flow path components, get you ready for, their specs and how they define very, very well. They define each and every component, but you need to know what they do. And that's kind of the focus here is what do each one of these components do? Okay. So this is a picture of a stage, and I've said the names, but here it is if you ever need to reference it. Okay. I don't think there's anything else that's shown that needs a picture or it needs a name other than maybe the shaft. Don't forget the shaft is under. In Duisburg, they call the top, the return, what we call a return bend at Dresser Clark, Dresser Rand. We called it a return bend. Some people call it what is it called? Turnaround. Yeah. And there's another one with channel in it. Duisburg calls it the 180-degree bend. But no matter what you call it, it has a purpose. We're going to get into that. I don't want to go into those slides. down at the bottom, the inlet guide vane, they would call that the 90-degree bend. Did you guys call it the guide vane section?
Yeah, but we got away from using guide, so.
Okay.
We build it into the exit angle of the return channels.
Right. So you just call the return channel all the way down to the impeller? So he's saying they kind of got rid of using guide vanes in Cooper, but I will say in my worldview, there is still an inlet guide portion to the flow path because the inlet guide portion does a certain function, and we'll get to that when I get to the slide. Okay. Here's yet another representation of this. I like this. Tang had this in his presentation. I thought it was really great because you don't often this. I was about 50 years old when I saw this for the very first time. I kind of got that impression over a lot of years of doing this, but this is pretty neat. So there's a P total and a P static. P static is in green, P total is in blue. So you go, what's static and total pressure? Remember, I'm not a smart guy, but just remember, static pressure is what you might measure with a gauge, right? Total pressure is if you get gas moving, there's energy in that gas. So there's a total pressure. I never got to the point where I understood it. Doesn't matter to understand it because you can make it through your entire life without understanding. John probably understands it, but we won't get into it.
The pressure you get if you stop.
If you stop the gas, right? So it has energy in it, has work put into it. So the gas goes really fast right here at the exit of the impeller, okay? And then through the diffuser, what are you doing with the diffuser? We'll get to it, but you're slowing the gas down to recover pressure. It's called pressure recovery in that device. And so you see the total pressure goes up massively once the impeller has imparted its work to it, but the static pressure builds slowly. Depending on how you build those stationaries, I think that static chart changes a massive amount because we have really screwed up some stationary components. So we're going to take a look at some of that stuff as we go through. But this is a representation of a compressor. They labeled the stations a little bit differently because their one was a plenum and their 9 is the guide vane at the end. Kind of like the Cooper does because they have that 7 is at the top, just like John was explaining. Okay, so the very first principle of compression performance, get the gas in. So there's an inlet flange, whether it's oriented up, down, axial. It could be coming straight in. If you have an overhung compressor design, you have to get the gas into the impeller. That happens primarily first through the inlet flange. I think it's really important. Not everybody does it this way, but I was taught this way to evaluate flange Mach number. Mach number is just how fast you are moving in relation to the sonic velocity or the speed of sound of that medium that you're trying to compress. So we use the KZRTG of the gas. It's usually like for air, I think it's like 1700. And we say, how fast are you moving? If you're above like 0.13, okay, so this is a graph that gives you Mach number. If you're above about 0.13, you have to start taking more and more loss. You will get pressure loss through it. It's no different than flow through a pipe, okay, because that's primarily a pipe. So we have a little loss coefficient thing. Other companies don't do it this way, but this is how Dresser-Rand did it. And they used to say a velocity head, their little terminology for it, was synonymous with 155 feet of head loss. And you say, well, how do I calculate? If I have just static pressure and I have gas sitting here, what's 155 feet of head loss? Yeah, that's a pain in the butt to calculate. So we're not going to try it. There's software that'll do it for you. Okay. Inlet and flange and inlet plenum. Okay, so they work in concert, and we often think of it as one thing. Duisburg does not. They break this thing up into many segments, coming into the flange, going through the splitter vane, the area coming directly in the first outer radius of the casing. Then they look at the area as you split the flow in two pieces and you go down each side of the inlet plenum. Then they look at the entrance of the inlet guide vane where the orange part starts. It's a lot, but they do that because you want to speed gas up and slow gas down very evenly. You don't want anything to turn. You don't want to go around a 90-degree bend inside a compressor. That's less efficient and you get pressure loss, just like flowing a pipe, okay? So you're going to see things that I term it as called sexy. The sexier it looks, the better it is. That's just the way compressors are. There's no other way to put it. Yes, Joe. I call the inlet plenum basically the blue part and the white part immediately under the blue part until you get to the orange part in the picture. In the photograph, it's the black part. So we don't show on the photograph on the right, we don't show, hey, what the heck? Let me get rid of that for you guys. Okay, so on the photograph on the right, they don't show the inlet, right? They're just showing the plenum, and that's the cavity that's totally black. Okay. More views. I like pictures. They say pictures are worth 1,000 words. So I've got about 5 billion words in this presentation because I just went and got a lot of pictures to talk about. There's the words on the screen. Okay. Let me basic down. Splitter veins, plenum veins, Seagull veins. There's a lot of variation in these designs. These are some old ones, but they were very important. This was a high flow machine where they had performance problems and the separation of the gas. They used to do it this way. I've seen many configurations of having these additional plenum veins in there. Sometimes they need to split the gas. And it really comes down to the designer. There's different aero people, there's different product people. There's reasons to put this stuff in. I won't say that I was ever privy to all of the thinkings of why they did it. I'll show you one picture in the next slide of why sometimes they're put in there. But if you see this, the innermost set of veins that looks like a little star, that, well, it's a weird star, but like a star with many points. That's the inlet guide vein portion. Immediately outer of that is a set of veins. Let me see if I can point at it. So this set of veins there, okay? I want you to note the shape of those because these things, I called them finger veins. I think that was kind of like the dresser terminology for it. The finger veins, you're catching gas as it goes around the plenum and it's uniform, but it's not all in the same direction. As soon as you get inside of the guide vein, right, you can see these are all uniform. But these finger veins, they have to have a little bit of turn to capture the gas. Okay, the splitter veins at the bottom down here, and that just, as gas gets to the bottom, it says, hey, stop going this way. I need you to turn and go up into the impeller, okay? So this is kind of what it looks like in visualizing the flow path, okay? The flow streams there, you can see it hits the splitter vein at the very bottom. Boy, my mouse disappears fast. This is not an awesome design, right? You get a lot of turbulence in flow. That would create a change in pressure differential that may get translated into the impeller. That would be bad. You don't want to see a change in pressure as an impeller rotates around. It's bad for the impeller and it's bad for the performance. I didn't finish the slide. That should get out of there. Sorry. But here's another picture where they said, hey, we're going to get rid of the splitter vein and we're going to go to a Seagull. And that was a really popular thing that Dresser Rand did. We use Seagulls in all the datums. And I think it's a pretty good design. And if you, I don't have a picture of the flow with a Seagull, but I can envision it being way more smooth and creating less of a pressure differential top to bottom. Okay. This is a Duisburg compressor. And they're not using the Seagull in the new SVM. They're going to use this baffle plate, which I thought that's pretty cool. And they did enough evaluation that says they didn't even need a plate that goes up and down that stops it. The gas will figure itself out. But you can see that they have a variation, even though that's just an inlet guide. Okay, there you can see that has the finger vein shape to it. It's catching gas coming down each side of the plenum. Okay, and over there you can see in this screen where they got INLANE at the top of the plenum, and then they evaluate, okay, how much area do I have on the left, which is in dark red, or on the right, which is yellow, right? Gas will go both ways. So they're trying to trying to make sure that you have enough area that you don't clog that off. Getting the gas from the flange to the first impeller, you can treat that like a valve, okay? We're going to see something called movable guide vanes. You can literally put a valve right in your compressor, okay? So if you don't design this with intention to keep the gas moving smoothly and don't accelerate or decelerate too fast, you'll ruin the performance, okay? Another picture of that. And why I included this, and it's the duplicate, is that in Duisburg, in their specs, they started to put these rough guidelines in. So you'll see a few pages of this where they say, well, how much area should you have here? Or how much area should we have in the plenum? So they start giving some rough approximations in relation to the impeller eye area. So your first stage, this is the first component that you're actually gonna measure when you get into Smart Perf or any other performance program. You're gonna say what's the capacity the customer needs, and you're gonna take the volume and you're gonna size the impeller for that. You're gonna try to determine a total speed and set a capacity. Q over N is the measure for the first stage. That area of the impeller, working backwards, if you're new equipment, sets the size of the plenum, the inlet guide in front of it, and it'll set the size of the flange. You can say, well, Greg, you said make sure the flange is big enough when you start. Okay, but that's not how they do it in new equipment land. They size the impellers first, and then everything goes backwards out to compressor. Okay. Another closer version of that, and you probably live in the world, product people see this through the design of the compressor, is they'll measure the area coming through that inlet guide vane. So this one has a little horizontal dash line. To me, that's the break line of where you've got the finger vane part and where the guide vane part takes over. So the primary purpose of an inlet guide. Now, this is the first stage inlet guide. We're going to get to it again when we get to the inner stage, right? But this is the one that's coming through the plenum. The finger vane portion of an inlet guide vane, if you don't have a separate plenum vane, the plenum vanes would be capturing the gas that it's going around the outside of the plenum, right? It's even, but it's different orientation depending on which vane you are. So they have different shapes. Just like this, target linear area distribution. That arrow points toward the portion of the inlet guide vane that may have the finger vane portion. It may not be uniform. Each vane would be different design. But once you get to the dashed horizontal line through the end of that vane, this is the 90-degree bend portion. And you say, Greg, that doesn't look like it's turning 90 degrees. Okay. But it's going to turn 90 degrees because we want gas going into the impeller directly into the face, parallel to the shaft, if we can get it there, right? But like it's going 100%, like along this side of that page, along this view, right? This is the area that they're measuring on the left, is the area distribution as you go through the inlet guide vane. The purpose is to take flow that's directly down in this page to directly left to right in the page. Okay. Now there's times that they don't. The finger vanes, we've been talking about that a lot. That's when the gas is not going directly straight down the page. When you get to the end of a diaphragm, you're going to see a difference in that guide vane because the return channel that presents the gas straight into this guide vane portion. The guide vane also may decide not to keep the gas straight, okay? And I've got a slide on that. The plenum area and the inlet guide, when you need to take up some axial stage space in a compressor, this is primarily for revamps or for new equipment that has a future build. I've seen compressors with extra stage spacing built into it for the future. Here's some examples of what that looks like. They're bridge overs. When you have bridge overs, you need to take additional loss. Flow through pipe, the pipe gets longer, you get more loss. In Dresser-Rand term, we would have a velocity head duration per stage of bridge over. So, well, how long is a stage? Yep, it's an art form to some degree. Okay. If you want to make it a science, you could say, I'm going to do a CFD of this bridge over, and I'm going to make some decision points in the contract to decide what's the lowest amount of loss I could get. That's an awful lot of effort. That's an awful lot of time. And if you're going to do it, I know engineers, they love to change something. So you come up with a concept, you do the CFD, you say, well, it could be better if I did this. Well, that is more time. You might already have your parts on order. If you want to make a bridge over that looks like this, your long lead, the top one, the top picture, I won't say this. If you're going to make a bridge over that looks like the top picture, that's a whole mess different of material and cost than you do if you looked at one of the bottom pictures, right? So you can't CFD this and conceptualize it during the contract. You can, but it slows up the contract. We like to build what we build, and we like to build what we bid, and we like to build it immediately. Okay? So just be mindful that a lot of the shapes that you see compressors, they're thought of by a guy that's just making a selection, and you go, okay, we'll deal with that later, and I'm gonna take X loss. And then some poor guy, mainly the people I'm talking with, is gonna be stuck with building it, right? And you have to deal with what you can do. You have space constraints, especially if you're doing revamps. New equipment has some, and this is why I wanted to talk about it on the slide. New equipment has some rules, like T-cell. I've heard this in the last few years. Oh, this is the way T-cell puts it out. That doesn't mean it's right. And I'll just say that. I want you to be mindful that if you can't get the gas in the compressor and to the first stage without a lot of loss, you're not going to be successful. So if T-cell gives you a guide vein and it doesn't look like it has a lot of taper like the leftmost, this is what we call the low loss bridge over. Karen, anyone that knew Karen Travastis, this is a low loss bridge over. She always said it, low loss. I meant it's many times she said this has to be a low loss bridge over. If I had a nickel for it, I'd be a millionaire. She loved the low loss bridge over. I said, but Karen, it costs so much. I don't have the money in the project for this. It's going to be low loss. That's the end. She was just, you can do whatever you want, Greg. You can make any marketing decision you want, but I'm going to make it a low loss bridge over. Like, okay, Karen. And we would put $100 in there and she would spend $1,000 every time because she was the arrow person. She gets to say, and why? Because she knew that if you couldn't get the gas into the first stage without ruining the performance, you're not going to get it out. Period. One of the biggest problems we had in the last 24 months in this was somebody took the T-cell inlet guide vein. This sucks. That's about as far as letter words I can get to without swearing and having to pay it out. But it's terrible. T-cell doesn't mean it gives you the right answer. It just gives you an answer. So you, as any portion of the design team, has the authority and you have the obligation to ask the question during the thing. They put a layout in front of you. Honestly, guys, the ones that I've seen, I don't get to see them until there's a problem. Someone says, "Oh, we failed test," and they bring me a layout. I say, "Show me what you did." It took me less than 20 seconds. They, well, why didn't you sit in the design review? I said, why wasn't I invited to the design review? Because I won't put up with it. And neither should anybody that's listening to me. If you see something that looks like a valve, you see something that pinches the performance, pinches and then expands, say something. You can see in that top picture, that plenum is huge. It doesn't speed the gas up until it gets to the impeller. I'm okay with that. You say, well, that's not a very pleasant looking plenum, but I don't care. It's big and then it gets small. It doesn't get small and then big. Okay? And it's that simple. I don't know the equations. I'm not talking Bernoulli's. I ain't talking any high fly. If it doesn't look sexy, it has to look sexy. And you say, well, my sexy is it gets small and then big. Okay, you're in a different. I'm in centrifugal sexy, right? You got to know where to make it small, where no to make it big. And inlet guides are not the place to pinch flow. And I've said it enough. I'm going to move on. Did everybody get it, or do I need to say it 3 more times? Go ahead, Joe.
But I like the analogy. So if I may just trying to understand from my perspective. So are you saying that the middle portion, first one, second, way out,
The middle one on the bottom.
middle bottom, are you saying that is more preferable, right?
No, that's a high loss bridge over. It's a low cost.
So then so what Karen was saying is ultimately good, are you saying?
Yeah, Karen, okay, everybody has their role. Karen was a performance person only. She didn't have to care how much it cost. She didn't have to sell it. She only had to make sure the performance first pass yield on test was 100%. That's what she got measured on. Right? Some other person has to build it faster, cheaper, with less material. Some other designer has to say like this. If you look at the left one, you see the ridges on the shaft? See how that bumps up? Boy, somebody had like something weird for breakfast that day. Why did they do that? Right? But some design engineer was doing aerodynamics and he says, I can't get the dang thing to pass for dynamics. I need it more stiff. And so he's like, where do I have room to make it more stiff? Can I change this? Can I change the impellers? And somebody said, well, they already sold it. Sorry, you can't change that. Well, okay, but I can't get it to stay in the bearings without tearing the bearings up. I have to do something. They use that area. You'd say, why would we ever do that? Well, because the design engineer said, if you don't spend the money to make that shaft look funny like that, it's going to tear the machine up. And if he didn't say that, and somebody just did that for fun, boy, that's an April Fool's prank, because who would make a shaft that looks like that, right? Unless there was a reason. Okay, so Karen's reason was, is my job to make the performance as good as possible? Sometimes that answer was no. Sometimes, Karen, we appreciate your opinion. We know you're always trying to take care of us the best you can in terms of aero performance. She didn't always win those conversations.
So, before this,
Yes.
people, have been driving like
Guys like Peyton. Yeah. Guys like Peyton will sell you up the river. Yes. So Job is asking for those online. I don't think they can hear you, Job, so I'm going to repeat it. But Job is asking how you make the decisions and why you would make the decision up front and then tie our hands in the contract to not have a change going forward. First, a good person tries not to, but it's impossible. I have actually sold a job where we purposely, the customer said, hey, we're trying to reduce head out of the compressor. Well, one way to reduce head that the compressor develops is to put a big old pinch on the inlet, right? And it's like making a suction throttle valve on there and say, okay, now this thing is making a lot of head, but I'm taking head out and I'm going to put it back in. And the customer was happy with that. We sold them a high loss bridge over. I literally put in the proposal, high loss. I put it in capitals, must be high loss bridge over. What did Karen advocate for? Right? But if you do it as a mistake, of course, we can have oversights. We've had some where, that's why I say, look at the Mach number of that flange, because if the Mach number's 0.2 or up, you've got an issue you have to deal with. Don't ignore it. We've had jobs where we've ignored it or just, it was an oversight. We didn't mean to overlook it. We just missed it. And then you get into this design cycle when everybody's in the, hey, we got to go. What's the lead time? When's that first rough drawing coming out? And you go, hang on. We don't know how we're building this yet. Right. And I do have those same conversations with, we lay out things that look like a datum all the time, but sometimes we shouldn't build things that look like a datum all the time. Sometimes we need to say, how will we build this? Will we build it with a return bend? Will we build it with stacked diaphragms? We need to have that discussion. And I sometimes don't have the time to have that discussion up front. Sometimes it's not worth it. We only sell 1 out of 20 projects. So you're really going to engineer to the nth degree every project? It's kind of a weird discussion to have to this slide, but it's great, Joe. But it's a good question. Okay. So there is no right answer. And people like Peyton make mistakes every time. He's a mistake magnet. And, sometimes, we give him a lot of grace because he does a really good job. He does the best he can. But that's where the learning cycle, okay, you guys are at the end of it. We got to have meetings like this, but maybe the meeting after this where we get together and we talk about it and we go, hey, did you know that we just went through this hell because you did this and you overlooked that? That lessons learned thing has to happen more often than it happens today, right? Because that's the only way we get better. And you need to wrap that cycle into the guys that are selling you down the river. We don't do it intentionally. Honestly, we don't, right? But we often miss the design cycle pullback, okay? Just because you have our bosses in those meetings and they're getting yelled at doesn't mean that we get the message. So get it to the AEs. And if you don't, find a way. I mean, Peyton, he loves setting up meetings. He lives for it. So just tell him, hey, we're going to have a discussion about it. Because honestly, I think we should have more discussions like that as a group, as a team of engineers, and not let the bosses, well, you're a boss, Job, so I can pick on you, but we can't let them do that. Okay. I would never put this in. We're talking about basics. This is something that's not really in every machine, but it's in an awful lot of them. We're taking out of most in Ingersoll Rand machines that had them, we're taking it out. But I thought, hey, I'm collecting this information. I'll just put it in here. I don't want to talk about a lot. Movable inlet guide vanes. So you could adjust, right, how much flow you're letting through the compressor. right? You can say, I'm going to give it a little bit of a with rotation or against rotation. I can close it off. It can actually act as a suction throttle valve. If it's the only vane or if it's in that middle position, the adjustment is done at the end of the guide vane. You can actually adjust the pre-swirl that enters the first stage impeller. Okay, so if you're adjusting the pre-swirl to the impeller, you're going to change performance drastically. If it's like the one on the left where it's a green picture before that blue thing, somebody should ask what that blue thing is, but if it's way up there before the inlet guide vane portion, then it's more like a finger vane and it's more like a suction throttle valve. You can close it down and you can pinch it off. So I like that curve at the top. Makina knows what I call that, but it's called the generalized movable inlet guide vane curve. And I'll let Makina tell you what I call it later over beers. But that is an Ingersoll Rand thing. And you can see in the little lower postage stamp there, it has that blue from the picture with the green, blue, and the red. It's got that blue thing in there. The blue thing's called a power wheel. Everyone's asked, what is it? It's an inlet guide vane that's actually stuck on the shaft and it rotates. If your mind's reeling like mine is, you're going, how would that work? Okay, but a compressor run backwards is a turbine, right? And you got expanders. You got a steam turbine that puts power into the gas, and you got expanders to take. So in theory, that guide vane, it's taking energy out of the gas, but there's not enough energy in that gas to really extend. So they just decided that, I think, and no one, goes way beyond me, probably goes before John, it goes before the people that I learned from. But in 1920, Ingersoll Rand did this all the time. Okay. And if you come across these, we try to take them out now. But as you change that finger vane portion, the green portion, you would change the velocity triangle coming into the impeller. And I think what they said is, well, if we have this power wheel, the blue portion, and it's moving with it, maybe they have a better incidence angle over a longer period of time. I don't know. I just don't know. And so there was a period of time when people say, well, we have to represent this in performance. And we tried that for about a year and then we got out of it. We just said, you know what? The power wheel does nothing. We have to break free from the insanity. And so we just got away from that. We still do the curve on the top right. If you have a movable guide vane that looks like the green one, this is real because you're basically doing suction throttling. And I've got a few more things talking about suction throttling and what that looks like. But is it increasing the flow coefficient? Yes, if you turn gas, and it's coming up, but if you turn gas against rotation of the impeller, it will increase the flow coefficient for the stage, not for the impeller.
But the blades in that rotating time.
The power wheel.
Yeah.
Yes.
They're fixed.
They're
So
fixed.
the angle coming into the impeller is.
It's going to be the same. Right. So how are they really getting the graph that shows such a variance? I don't know.
I mean, it's more or less effectiveness than your turbine.
Right. I would think acts more of a suction throttle valve.
Yeah.
As soon as you put the power wheel there, you've gone to making a suction throttle valve.
Yeah.
That in essence has a device that's hopefully what they're trying to do is make it a more effective suction throttle valve, but it's really not gonna change the performance all that much. And I think it'd just be super noisy. It's another noise source in my opinion. So this is another visualization of that. The black curve here represents a typical compressor that's using speed control. Okay. And so we haven't talked about these. We're going to talk about the terminology later, but you can envision the width of that map from the left to the right, as a certain size. As soon as you put guide vane control, you can start shifting your curve to have a wider range. That's really good in a industry that wants absolutely the widest range you can give it. So the guide vanes have a purpose and they should be sold more often, but they're not. They're only using single stage compressors. A lot of those in Duisburg where they're doing those 4-poster machines still, every single one of those has a movable guide vane because it's so integral. They can make a massively controllable compressor. They can run all over the map, right? By using these adjustments.
then the head.
The-
In the black.
If you adjust speed, right, so we build, what he's asking is why is the black one higher? So in variable speed machines, you can go up in speed. We always have a 5% margin. We sometimes have more. So there's always a higher head curve. Right. So you can actually get a variable speed with the green one, and you can move up and down with that. So if you have variable speed and movable inlet guide vane, you have a massive range of operating capability. Rubber, that's yes. But putting a movable guide vane in with a multi-stage, multi-section, or multi-stage machine, let's say if you had 9 stages, you're only affecting that first impeller. So you still have volume reduction effects, and we're going to start talking about volume reduction, and you'll see that it's not really conducive to putting, a movable guide vane on 9. A movable guide vane with 1 impeller, super, super productive, right? A movable guide vane with 9, it's not as valuable. Okay.
If you really want to get funky, do your single stage rubber compressor and then put it in tandem with another one. It's also set up
Yes.
that way.
Si-
And they
multiple
connect
single
series
stage-
parallel.
Right. Yeah.
That's-
On their own drivers, then you literally can do anything. Right. Yeah. So okay. A lot of stuff is on the slides. It's really busy. It's a concatenation of a couple of different things in the past. We just want you to envision specific speed, left to right, is what we call flow coefficient. I like that terminology a little bit better because specific speed comes with this equation here that's like h to the 3/4 power. I don't even know. Whatever. So the flow coefficient is how much flow an impeller passes. And you can have these really tall, skinny ones, they pass a little tiny flow. And then you get to the point where you can pass a massive amount of flow. If you're in datum world, you might know a 1207 wheel is a really popular one. That's like in this range. There's a point when you don't have enough blade in that to do enough turning to actually get a radial discharge, and then we get a mixed flow impeller, and that's like the 1653. They really got to the point where that's why I only have medium head 1653 impellers, because they just didn't have enough blade to get the gas turned all the way. So it was a mixed flow that we built a radial diffuser on. Okay, and the mixed flow impellers is where they say you start losing efficiency a little bit. Still very efficient compared to some of the low flow impellers. But there's that. And then this is the first time we start talking about loss buckets. I need to find a few more of these for all the other components, but this is the impeller loss bucket in terms of the size of the impeller, in terms of the specific speed, is that there's a frictional coefficient that gets higher the smaller it is. Then you think about boundary layer in your college courses, right? So you got a boundary layer. If the width of your diffuser is only a couple thousandths wide, it's all boundary layer. So you get a massive amount of friction loss on that stage and everything behind it. If you got a really high amount of flow, your diffuser is super wide, and then there's a loss called diffusion loss. And that goes like this. So there's a bucket, and that's why the optimum efficiency range is somewhere in the middle. Now, I don't pretend to understand what diffusion loss is, and I can just envision, okay, when I get to an axial flow impeller or an axial flow set of vanes and blades, there's no diffuser. But I guess in theory, it's a stator, and that is a diffuser in some sense, because you're changing the gas and you're slowing it down a tiny bit, but maybe what they're saying is in axials, you don't have enough length to actually slow it down. So there is a diffusion loss. But this is the graph I've been looking at it for all these years, and I never really thought too much about the diffusion side. I just go, oh, there's a peak, and it's right in the middle. 1207, 790 family, that's where your peak efficiency is. Some pictures of this. Impellers can be shrouded and unshrouded. If it's unshrouded, you're going to make the shroud with the stationary component. It's going to be part of the diaphragm. It's complicated, but you got to have that very tight. You have to have the surface, the rotating and the stationary surface very, very tight, or you'll lose performance. Okay. Okay. 2D circular arc vane shapes. I tried to get some pictures of this. I like this. Tang had these see-throughs. So 2D, they're very simple. You can put them on a simple milling machine. They're easy to make. Sometimes hard to put together, right? You can't reach in there with a weldment, so you're going to use like slot welding or EB welding or e-brazing, those kind of things. Just another visualization. Keep you on that visualization curve. There's the elements going through it. Okay. Here's some 3D impellers. I want you to learn a word called induced. A fully induced impeller has this leading edge is all the way out, and it's often straight up and down. So if you look at it in this view, it would be straight up and down right at the nose of the impeller. That'd be a fully induced impeller. 2D circular arc is almost never induced. Like this is partially induced, or you could have these impellers that's not induced at all. Like it's, if you look at the cross section, the vane starts once it starts turning radium. Okay. I don't have anything more to say about that. Jim Sorgas used to call arbitrary blade shapes. I'm sure that was his own term, but he talked an awful lot about that. And he would talk about blade shapes, and he would say, oh, what impeller? And he would want, and he had conical, he had several different terms. I'm not well versed in that, but I heard them all my life. I know that the arbitrary one, that's when, if you get into Duisburg, they call it the knowledge based, and they've got these veins, and they're all doing this type of thing. When you get to high flow, high efficiency, you're going to see an impeller with a lot of back sweep to it, and the more back sweep, it changes the head profile, changes the efficiency. One of the things, I think, was it on that slide? The only rotating aerodynamic component, and it's the only component that adds energy to the gas. Okay, so that was the key from that slide. I went past it. So the impeller is the key. Jim Sorkas used to say, impeller efficiency. Does anybody have a guess? But I'm sure you understand that it's higher than a stage efficiency, right? Because it's really good efficiency. It's not 100%, but it's like 96 is an average impeller efficiency. The stage behind it will drag it down to sub 90. But the impeller itself is really efficient. Okay. Some of the things that drag it down, let's start talking about this. Diffuser vanes. What is a diffuser vane for? It accepts high velocity, high kinetic energy gas from the impeller. It begins to convert it to static pressure. It does it by slowing the gas down in a very controlled manner. First and foremost, as the gas just leaves the impeller, it's going to go up in diameter. It's going to slow down naturally. Okay, so just through the diffuser, that's the thing. But then we contain this with walls in the diffuser passage and as a shroud and a disc side of the diffuser. And the diffuser can have shape. You may see some that look straight, and you may see some that taper. Okay, and that's the aero person going, I need to change how the gas is slowing down. Okay. Tang had this one. It was big for him, and I think this is important. No negative overlaps. So you don't want the impeller, you don't want the gas coming off the back side of this impeller and slamming into a wall. That will ruin performance. So alignment's critical. As you can envision, the more and more narrow that impeller gets, the more critical the alignment to the diffuser is. If you're in a back-to-back compressor, it gets near impossible to get alignment to all the stages. Okay. In the picture on the left, it's picturing a vaneless diffuser. In the middle, this is what I call a wedge diffuser or a full diffuser type. It can have a wedge design. It could actually have an airfoil design. It could do some different things. And the top in the middle is an LSD, a typical LSD. That stands for low solidity diffuser vane. And I'll just explain it here because we can visually see it. In the bottom right is an airfoil LSD. So the way that you can tell it's a low solidity diffuser is if the vane, if you envision the vane, I got a point. So if you envision rotating this vane around its outermost diameter, if you rotated this out, if the nose, the entrance of that vane would hit the exit of the next vane, then it's not low solidity. It makes an arc and would make more. What solidity is how much blockage the path has, right? So low solidity means it has low blockage. And you can see here, this one might not be an LSD. If you swung that up, it might hit that, but it's pretty LSD looking. Okay. So the shorter those are, the more confident you can be that you have an LSD. And Jim Sorkas, he loved that term because it sounded like a drug that he took when he was a kid. He didn't take drugs, but LSD, the drug. Engineers have funny ways of amusing themselves. Okay, flow visualization. So this is another picture of the LSD or or diffuser vane, however you want to call it. The one on the right is an airfoil. The one on the left is a straight vane. They can have any shape. I think it's more traditional to have the airfoil shape. And then we saw some airfoil shapes coming with actually like a curve to them, right? This was more of a straight airfoil. But the two CFDs here, they give you an impression of the pressure profile. And I want you to understand two concepts of this. Put an LSD in, you're going to see in the next series of curves what it does for you in terms of performance. That's what we're here to talk about, right? And you can imagine it's going to make the performance better. If it didn't, why would you spend all this engineering and effort and cost putting these features in if it didn't make something better, okay? But it has a negative, and here's the negative. You can see how the pressure profile moves all over the place, okay? So when pressure goes high and low, you have alternating stresses. You also have a lot of noise. Got to remember the gas is flowing at its highest velocity at this point when it enters the LSD. So this is generating noise. This is where the DRA comes into play and why we need the DRA, okay? Also, this is the first time I've actually shown a nice visual of the orientation of the gas as it leaves this impeller on the left. Where the little blue swipe is where the gas leaves, and you can see the trailing edge of that vane. It goes off in the exact direction of that vane, of the LSD vane. Okay, so that's the first time you have a flow visualization of reality of the way that's going. And you can see the blue and the green swipes at the top on the left. I say in the top, where is that? So that's here. So that's the flow path visualization of the way the gas goes. And you can see it's turning over, right? As it slows down, it's going up and up and up in diameter, and it slows down. The tangential component of its velocities, nothing's really imparting any change to it, but the radial component of that velocity is slowing down because the area is increasing, okay? That's why it appears to change directions. Just some more pictures of vane. I don't want to belabor this. This is just for reference in this training material. If you ever open it up and say, hey, what does a vane diffuser get me? It gets you better head and it gets you better efficiency. This is a vane, full vane. This is a low solidity. Almost the same type of behavior. One thing that chart doesn't show, and this is not, I don't know if this is real data. This is someone's depiction of it. But if a vaneless pass, okay, gets utilization of the entire flow range of the impeller, a vaned pass is going to shorten the range. It must, because there's an incident. So I don't have the loss bucket. I need to find the loss bucket in here. But incidence angle of the flow leaving the impeller, hitting the vane, there's a design point. That'll be in the middle of the curve, probably at peak efficiency. As you change this flow rate that's going through the impeller, it changes the incident angle that the flow leaves the impeller, right? So the incident with that vane. As you change the incident angle, you're going to get more and more loss, right? Because you don't want to turn gas rapidly. Well, you can imagine smacking into a vane that's at a totally different angle. That's changing the gas direction rapidly, okay? So we give you a little happy, sad chart for vaneless, vaned, and LSD. And imagine that the more you do the turning, the more you lose the range, okay? Here's another picture of it, of a ribbed diffuser. And that's a terminology when you don't have it all the way across the channel, then we call it a rib diffuser. Usually used for super high flow impellers. Okay, 1653 family has it as a default. You can't even build them without it. Okay. And then one that doesn't exist, I've never seen it, but in theory, it makes even better efficiency. So if you compare these two plots, this gets you quite a bit more head. When I took the Gepixi class, they talked a lot about vaned passages. Okay, so if you think about that wedge diffuser, if you look at the compressors in the solid rocket boosters in the spacecraft, they have a very specific duty and they have to have the absolute most efficiency, period. And they're literally running out of point. They start it, it fires, and they just compress. And then they need to get the payload into space with as little gas as possible, right? With fuel. So they use a completely vaned passage. It goes up the diffuser, over to return bend, down to return channel, all vaned, because they can peak the efficiency and they lose all the range. The range is gone. It goes up and down, but they get that extra 0.25% efficiency. That's what they need. So if you look at rocket fuels and rocket compressors, they're built with fully vaned passages. We are doing process equipment. They want wide ranges. They want wide everything. But efficiency is sometimes important. When efficiency is important, we use LSDs. Or if we're short on performance and we think we're going to fail the performance test, we use LSDs. So we use LSDs a lot, right? Because it's a catch-all. It's easier to sell a revamp if the efficiency is high too. Next flow path component is called a return bend. The turnaround, the 180-degree turn, whatever you want to use as the terminology. Its purpose is to take gas that's leaving the compressor. It's going out. It would just go into space. We have to turn it around and we have to send it back to the next impeller. So that's all it does. It takes gas that's going out where it says B5 and it puts it in where it says B6. Some of the components that you'll see in a return bend is this bulb that's on the diaphragm. This picture is of a very large bulb. Doesn't have to be that big. And you're going to see some examples where they're much smaller. Also, as you slow the gas down, it's still diffusing. The area is still increasing as it gets to the top of that bulb. If it's still diffusing, it means the gas is still slowing down. If the gas is slowing down, it means that you might have more volume in that gas, right? So they usually typically want to increase the area to promote continual diffusion. A lot of times you'll see, if you look at datums or old compressors, you may see, oh, my mouse is moving on its own. You may see no increase in area from the left to the right side of a return bend. Don't be alarmed. It's dependent on a lot of things, okay? Gas densities, what we're doing with the gas, the pressure, the volume reduction, all that plays a part. You can see this as high as 50% increase, and you can see it. I've seen them actually where it pinched, where it was 90% of the passes on the left. I personally think that's a mistake, but the guy that did it is not alive. I couldn't ask him.
The Cooper rule in the 80s.
Yeah.
Was to slightly accelerate the gas.
Slightly,
and
sorry.
turn around. The idea was to keep control of it.
Okay, so John is saying that Cooper rule
Till
till
1997.
1997 was to slightly increase the gas to keep control of it, air quotes.
And if you see all the performance curves, they're all choking early.
Oh, they choked early because of it. Yes.
Uh,
I'm going to show you one of our, what we call the ugly diaphragm that's coming up. And we did the same thing.
Hard way on a machine that eventually
Right.
got replaced by a dress around machine.
Okay. Wow, my mouse is moving on its own. Yeah, and that's the other thing you have to remember is the next component when we get to it. You need to know the angle. Whenever you're going to put gas to a vein, you need to know the angle of that gas so that you have an incident angle to it. The return channel has a vein. We're going to see that in a second. So if you open this up massively and you're going to see some old designs, you lose track of what angle that gas is doing, right? So I like the idea of controlling it. You know exactly what angle you're going to keep, and you want to maintain that angle so you know how to build your return channel.
Except the velocity of the too high.
Yeah, you don't want.
And
Yeah.
and as it's going around the top of the turnaround,
Yeah.
we were getting flow separation, and actually
There you go.
way too much.
And that flow separation John's talking about, he says, as gas comes around this turn, we get flow separation right here. And we used to have a lot of surge events that initiated in this area, and then they roll backwards. Actually, it comes back into the stage prior to it. It can go downstream or upstream, but yeah, you don't want to initiate surge because it propagates through the rest of the stage.
We just choked it.
And choke error is what John's saying is choke is the bad problem here because as you created a reversal bubble, you're losing half of your flow path. And if you get separation and choke, you're losing flow path. And so then you get even narrower path. So one of the things, we have a slide on this about reducing this bulb, and you'll know, I think datums are really, really generous. So you'll hear an aero person say, oh, that's a really fast turn. But you remember that the gas is not coming in and out of or coming directly along the page. At B5, it's got an angle, probably about 60 degrees in and out of the page. So this turn, if you think about it, if gas particle goes here to here, it's not going around, let's call that a 1-inch radius. It's not going around a 1-inch radius. If this is a 20-inch diameter, if R5 is 20 inches, the radius that the gas is going to see is closer to 20 than it is the 1 inch. It doesn't go straight up over that. And I try to remind Karen, as she would be totally conservative. I would start it off with a diss, right? You say, you're too conservative. That's how you win every argument. And then I say, you got to remember that the gas isn't just going over that willy-nilly. And then she would just kind of look at me and roll her eyes. And then I would go get a picture of where we made these bulbs, like 1/10 of this in the picture. And I'd say, well, you built it this way. She goes, I had to than that one. I'm like, well, I think I just won the argument. So anyways, diffuser, what that did not show is that the height of the diffuser, what we call the diffuser radius ratio. So it's the in that picture before, it's the B5 divided by, or the R5, sorry, divided by the R2, which is the diameter of the impeller radius. If you're using R's, it's radius of the impeller. But whether you use radius or diameter, if you take that ratio, you get a radius ratio. And if you are somewhere in the 1.5 range to 1.7 range, you're in that sweet spot where most impellers and most stages can live with it without a major problem. When you get to really flow coefficient stages, you have to start reducing the diffuser radius ratio, okay? And the design of like the 275 HBA drops the standard from 1.5 to 1.42, and then if you go to the really small flow coefficients, it goes to 1.35. Duisburg has had a similar chart here where they say, here's the optimal based on flow coefficient. What we do here is we just get a correction if you make it too short. We live in the revamp world where we don't want to make them long, right? We almost never have that space. We're almost putting 10 pounds into a 5-pound bag all the time, right? So we shorten diffusers. So we put a natural duration into this to slow the revamp engineers down from being too optimistic, right? We have to put some duration in there for those stages. So that's just a chart to remind you. If you get this presentation, we do have a shortcut to this tool that allows you to lay out the stage and then predict your diffuser radius ratio. Moving on. When we leave the return bend, we get into the return channel. Its purpose is to remove tangential velocity and swirl that was put in there by the impeller. And we return the gas to a radial direction. And it's going to be radially toward the shaft, so directly inwards. In this picture, this red on the left, it says view the diaphragm return channel from the right to the left. That red line shows everything that we would call the return channel. However, after the line, the horizontal line in that channel, oh my gosh, right here, after this line, this is the inlet guide portion. So even though the red line is there, the return channel, in my world, the purpose of it is only going from this top line, the entrance, to the exit. And here you can see this is a datum one where there's two sets of vanes. The return channels are what I call the banana vanes. They are symmetric, they're all the same, and they go right to that horizontal line. And then the inlet guide vanes are every other vane because you have too much solidity. So you reduce the vane count, okay? On the top picture, it's a little easier to see in isometric, so I include it there. And you can see that the guide vane portion goes on with every other vane being a guide vane. In the photograph on the bottom, this is an old style where this was non-datum, but this was the return channel for an older style compressor, and you can see that only the banana vanes are there. Also, the pressure profile on the leftmost picture says return channel field of off design using unsteady CFD. So off design, so someone was studying, are we going to have a surge event or an overload, a choke event? So whatever they were studying, that just gives you a picture probably of a pressure profile. Okay, visualizing the flow, because that's part of this. On the left-hand side, you have a dashed red curve that represents the dividing line between the impeller and the diffuser and return channel. On the left, you're seeing the diffuser portion, and on the right, you're seeing the back end of that diaphragm. That's the return channels. You can see the banana vanes. So from a flow visualization, just know that inside the red circle, it's visualizing that impeller in reference to the impeller. So it's rotating. The gas goes down the vanes. That's why it seems to appear it goes counterclockwise. In reality, it's the gas itself is moving clockwise in our frame of reference. So outside of the red circle, you're now in a stationary frame of reference, and that's why you go back to this flow visualization where it goes clockwise rotation as it moves out. Okay? Probably hard to see, but this is the flow visualization. It goes here and it goes out. It goes up over the return bend, and it doesn't change direction. It's continuing to go clockwise. That's why when you get to this side, it captures it clockwise, or it doesn't capture, but it turns over clockwise and it continues downwards toward the next shaft. The banana vane has an incidence. You can see that they're trying to set that vane angle equal to the angle of the gas as it comes over the top of the return bend. Okay, then it turns its radial by the end of that vane. The guide vane, why does that keep doing it? The guide vane would start right there, and it's going to turn the gas 90 degrees into the next impeller. Okay, I don't know why we demand the gas to be completely radial by the end of the return channel. Okay, if you're going to have a next set of vanes, just like the finger vanes on the inlet guide, why can't these have a little bit of pre-swirl and do the rest of the turning in that lower portion of the inlet guide vane? To me, I think it'd be acceptable. And why, only reason I mention that is because I live in revamp land, and often we have to go cram something in, and then we don't have enough radial height to get a turn in there. You're going to see this when we get to Duisburg and we get to Chescui. That's something they check on. They'll say, hey, you don't have enough return channel vane height to get the turn done. Okay. But they have a very tall in the guide portion. Okay. And someday we may have to deal with that. The way they got around it is they took this 2D approach to return channels. If you take this and you think about this being straight across the top, right here, you see these vanes, they come out straight. There's a 2D profile. So Duisburg's got a new 3D return channel profile. First time I've ever seen it. And it allows you to have a very short diffuser and return channel. So you can put a higher diameter impeller into a smaller compressor. Okay. 3D return channels, brand new. It is adaptable to datums. You can get those designs. They're putting them in the datums for SVM. So that's a limited amount of datums, but it can be adaptable to any stage.
We used to do
3D?
No.
Oh.
The 2D stuff said first.
Where we didn't
bring it radial,
turn it totally radial.
and then turn it with the guide.
Right.
When we had separate guide vane inserts.
Okay.
Okay. Then we got rid of the lead path by not having the separate guide vanes. And we would put whatever swirl we wanted into the trailing edge of the return channel vane.
Okay, so John sharing that at Cooper, they actually started using the return channel to determine the swirl. And we're going to talk about that coming up because I got another inlet guide portion. But yes, if you want it to be radial, you would finish the turn with the return channel and just not have a guide vane, right? It'll go around that bend naturally. You don't necessarily need the vanes. They're not doing the turning you need in the 90-degree bend. They really are just supporting. It's a mechanical function more than an aerodynamic function, where those vanes are just supporting the inner ring of the IGV.
If it works structurally, we might extend the return channel vane down into the guide vane area, but it wouldn't be a separate
piece. It was all, yeah. Okay. Inlet guide vanes. So this is the last flow path component before we talk about getting the gas out of the compressor. But in between two stages, the last component that you have in the flow path is inlet guide vane. We already talked about them once, so it's kind of the same thing. But as John and I were mentioning, they accept radial gas, right? And by Dresser-Rand definition, they're accepting radial gas, and they're going to turn it to being parallel with the shaft. That's the only purpose of an inlet guide. Okay. If you're doing something different, then you're in a different portion of the flow path. You're up in the return channel. Okay. So this is just the 90-degree bend, as Duisburg calls it. And the component you can see, let's say in the middle picture, on the left of the middle picture, where's my mouse? You can see a pretty traditional one where it comes down and it turns pretty quickly and it goes into the impeller. All the other ones in this, right? And on the left-hand side in the middle, that's a pretty traditional inlet guide. All the other ones are showing bridge overs. A bridge over here where we had a little, sorry about that. A bridge over here where we had a little extra space. A bridge over where we have to go underneath a volute and we have to have extra space to give that area here in the volute. A bridge over where we destaged and we have several impellers to go. Or a bridge over where we're slanting the return channel and then taking as little space as we can on the bridge over the inlet guide vane. Why? Because every time you have pipe length, you have pressure loss. So we want to minimize the pressure loss. If you can angle that return channel to get to the impeller, you should do it because you're stuck coming from the OD to the ID. If you can do that on an angle, you'll have less loss. Okay. Sometimes you don't mind the loss. And on the top picture, this is a high loss bridge over, and it's the lowest cost. You can see we can just go get a pipe and we can actually whittle that right out of a piece of a pipe. I mean, it's very simple to make this. And sometimes they hang vanes off of it. Sometimes they don't even. When it's super long, they like to hang a couple vanes just to keep the swirl out of the gas. It will pick up swirl from the shaft. So you just want to take it out right before it enters the impeller. So this is primarily done when you don't mind a little bit of pressure loss, a little bit of efficiency loss, and you need it to be cheap, right? So if a compressor's sitting there and a customer says, "Hey, I just need head taken out of this," they don't want to spend $1 million doing that. They want to do it as inexpensively as possible. The photographs are some traditional ones. On the top picture, you can see the end of the return channel vane, and that's the gray portion right there. So that's the end of the return channel vane, and then the IGV takes over. You can also see that they kind of sharpen that. Sometimes they're sharpened, sometimes they're not. Okay, I included the rough guideline for how you would size those. This is not scientific. This is just gives you some general guidelines. If you say, well, how big is that? I want to reduce the stage space. You may want to know just about how big that gets. It's always in relationship to the impeller following it, right? The impeller area, they go up the stage space to that A70 is labeled on that drawing. And then from the impeller downstream, you go through the diffuser, the return bend, and the entrance, the B6 or the entrance to the return channel. That's from the impeller downstream. So the upstream to this point of the exit of the return channel is upstream from the impeller, and then from the entrance to the return channel back is to the downstream of the impeller. That's what's set in the areas. Okay. As we've been talking about, you can shift the flow that goes to a stage, and this is the performance part of it. So guide vanes, you'd say, oh, that has nothing to do with performance. Yeah, until you determine to make it have something to do with the performance. You can shift the flow with rotation of the impeller, and you get less capacity and less head. And you can shift the flow with or against the rotation of the impeller, and you get more flow and you get a little bit more head. In both situations, I dropped the efficiency curve on these. I think the most efficient way to do it is to bring it in radially. I'm not sure. Don't quote me on this. You could go and run those calcs, but I don't think you really affect efficiency all that much at all. But if there was any effect, it'd be a little bit less, all in all, if you had to say there was any change. Okay. Now, the last component we need to talk about is getting the flow out of the compressor, and this is called the discharge volute. There's a couple of different types, but traditionally we like to use a scrolling volute. That means that at the one portion on the bottom middle, the black background, let's talk about that one first. At one point, you're going to catch gas coming up the diffuser. Where is this mouse? And you're going to have very little gas. So the very first element enters in here, so you have a small channel. As you add more gas, you need to make it larger and larger. If not, you're going to choke the flow, and that's going to have a higher pressure loss. So we size the volute based on the discharge flange. The discharge flange should be sized based on how much volume flow you have exiting the compressor. This gets a little bit complicated, and sometimes you can't pair the volute with the flange if you're in revamp land. So we have an awful lot of discussion about this, yet it's a science that we have just now started to do well. This in the last 2 or 3 years. Why? Because we've had a few of these projects where they were done incorrectly, and it made it very, very apparent that this was a key contributor to our performance downfall. Scrolling volutes are nice. We don't always find them. Sometimes you find a collector, that's the one in the middle. The picture in the middle, you can see it stays fat. There's more loss involved with that because you're not controlling the flow. That first element that dumps in is dumping in all by itself. So you have a huge area, so it can go anywhere it wants. So collectors aren't perfect, but sometimes that's due to cost or due to other situations that might be what you have to deal with. It's more lossy if you have a collector, and you'll have to deal with that by yourself or with an aero person. Say, what do you want me to do with this collector? You don't want to get involved with doing a CFD to do a collector. Just take an adequate loss and move on. It's just about making enough head to make sure you overcome that. You're not going to have a choke problem with a collector, in my opinion. It's as big as it can be. Then you're really stuck with looking at the flange, and we're going to get to that in a second. So its purpose is to gather swirling flow, because that was swirled from the impeller. It went through a diffuser, hopefully. It's still swirling, just like it enters the return channel. Return channel reduces the swirl. The volute does not reduce the swirl unless it has to, and that's a totally different device. But I have a slide on that. So it just collects it, keeps it swirling, and then it exits. It can exit tangentially, or it can exit, which most of those pictures are tangential. The one on the bottom right is kind of a radial. It's got a little bit of a turn to it, but tangential looks like this one here, where it stays at the OD of the stage. You can see two tangential discharges in that top middle picture. The inlet is radial. So radial just means that if you looked at the flange, it points at the center of the shaft. If it's pointing at the center of the shaft, it's radial. Okay. If it's radial, you have to do the turning in the volute or in that flange portion as it transitions from the volute into the flange. There are 4 different volute styles in the Datum playbook: internal, external. External, where you build it on on the outside of the case, and then the D is where you've got a case OD is huge, and then you just put the stuff inside. We've seen all 4 this style of volute, but it doesn't really change what the device does, right? It's still collecting gas and you're moving it. If you ever need to size in terms of a Dresser-Clark, Dresser-Rand design, everybody does this differently. We use QD over N. It's a dimensional, well, it's not dimensionless, but it's a variable that we use to say how big the volute is. And then we apply a lot of fudge factors inside the smart perf or cent perf that looks kind of like this chart. And we like the way we do it. We like our loading to be between 70 and 90%. That's where this blue little band is, saying that's the peak. And this is the curve, the loss bucket curve. If you get over a certain amount of loading, you have to make sure you have enough, correction for it. All of this correction that we calculate using the fudge factors gets applied to the last stage. So it just takes the mu efficiency of the last stage and multiplies it by whatever we say the correction is for the volute. You can screw this calculation up really easily. They're now transitioning. We're going to get to the area of the channel. We're going to get rid of the QD over N, and we're going to go to just saying how big is the channel and how big is the area of that. You'll see that transition. Chescui already does it that way.
Is that analogous to how Cooper did it, where we looked at an oversize ratio?
Is that how you did it? Oversized ratio is what you did?
I think
Okay.
it's the inverse of your loading.
Okay.
I don't know if it's the same equation.
I know that Duisburg shoots for 100% or more. So they're doing it differently than we do it.
Go no less than 110%.
110?
It could be
Okay.
50, 164
Yeah.
for
Oh.
volute.
Yeah, and actually, I didn't mention that, but that's a good point, right? So that we got these rule of thumbs for all these things, right? So whether you're Cooper, any company, right? Elliott, I'm sure they all do it similarly, but a lot of people, the customers will talk about velocity. They'll say, "What's the velocity in a flange?" I didn't mention that, right? Because you can't answer that. Depending on the gas density and the pressures and temperatures, you're gonna see different. If you're compressing hydrogen, you'll have a high velocity and it's not disturbing. But traditionally, 150 feet per second at a flange is the number I was taught at the beginning. In general, if you see anything over 150, 120 for you. And new equipment, they want it to be slow. Just make a bigger flange. What's it matter? It's a white sheet of paper, right? But in the aftermarket where I live, we're going, how fast can you go? We've had velocities at 300 to 400 feet per second. We've had Mach numbers at 0.2, 0.25 was our highest. Actually, 0.28, I think we hit on an inlet.
Some old Cooper facing designs, the exit nozzle could be 160, 170, 180. Business.
Yeah. So, yeah, when we get to doing it, there's an awful lot of discussion. We have whole training classes just on the volute itself. That's how crazy it gets. From our perspective of just general performance, you have to know one thing. You should be able to repeat. You have to get the flow out. Don't make a blockage, right? Whatever you have to do. If you have a radial discharge, like in the old IR blowers, you may have a radial discharge. And on the top portion, that's a datum up there. I put it as a thumbnail. It was a datum back to back with a radial inlet. And the customer didn't need 2 sections of compression anymore. We converted that to be a straight through machine. And we used what I call a reverse inlet. I don't know if it has a term. IR made these things where we put a diaphragm to take the swirl out of it, reduce, bring it back to radial, and then use a 180-degree bend essentially to enter it into a plenum, a discharge plenum that worked exactly like an inlet in reverse. That's why I call it a reverse inlet. No one's ever used a terminology that I like better, so it sticks. I will tell you that there's no additional loss over a typical volute. Some people will have you put an additional 2-3% of mu and efficiency loss on the stage. Okay, I'm going to point this out on the slide. Remember where we said a stage goes from the impeller to the impeller, right? So the stage goes from here to here. Well, on the last stage, whether you're going through a reverse inlet or whether you're going through a volute, your stage is going from this impeller to that flange, okay? And all you have between there and there is one calculation in Dresser-Randland, which is called the volute loading. There's a lot of stuff going on in that picture between the volute loading. In this case, your stage performance, you could say, is almost essentially done to there. So then all you've got to do is pick up that plenum from here to there. So in a volute where you're gathering the swirling and you're doing diffusion in the volute, there's a lot of different volute designs. You really aren't adding an awful lot to the stage. So if you have a 7 or 8% loss due to the volute, but all you're doing is going through that plenum, that's a heck of a lot more loss than you got on the inlet side of the compressor. Okay, so just be mindful of that, and no one will ask you what the discharge Mach number is. No one in 30 years of doing this has asked me that. But I got into the habit, if you look at my hand calculator, if we get time to go through that, I've got discharge Mach number, and I pay attention to that because it's flow through pipe. If you exit this compressor at 0.4 Mach, you should be telling your customer, I think your discharge pipe's a little too small, right? Because that's noise and that's loss. That's great that you got the pressure to their flange, but they're going to want to do something with that gas. Okay, so just be mindful of Mach number both in and out. That's all 3 components. Okay. Oh, I had a whole slide that said that. Okay, so that ends that section. Wow, I went for 1 hour and 43 minutes. I think we could end there, but I do want to talk a little bit. So I'm going to go hunt for a few slides just so that we can talk about performance curves, if you'll bear with me. Anybody still online? We're good?
Yes.
I'm on slide 47 of 998. So I'm just going to go through a couple of these things and go past them. I'm not going to talk about it. This section was about revamping, about improving efficiency, about fitting in more than actually fits in there. There's one of those really tight turns that I told you I argue with Karen about. This is where we change the configuration of a compressor to make what needs to be done fit inside the compressor. Angling diffusers back, shortening stages, you make it do what it needs to be. I want to talk about this one. So we've been talking about old versus new, okay? And I hope you can start seeing the difference between the top and the bottom. Essentially the same compressor, essentially the same. It's an ethylene refrigeration compressor, top and bottom. What might be done today is on top. What might have been done in the past is on the bottom, okay? And some of the things that you'll see that we shouldn't continue to do is turn things at 90-degree angles, right? That's bad. We've talked about that. That could create a loss. Now, I don't mind it because it's humongous area, but that should have been turned more generously. Today, we turn it very generously. And if you see T-cell pop something out with a 90-degree turn, or something that looks like it pinches the flow and then opens up like massively, there is no acceleration from here to here. That's not good. That's not good. You need to accelerate the gas as it enters the impeller. Okay? Also, this impeller being that high of a flow coefficient, we would never build not being at least partially induced. This one is almost not induced at all. We would not build impellers this way anymore. We build it like this, where it's fully induced. Okay? It's more elegant. It gets a better range, and it gets a better efficiency profile. Diffusion, a lot of taper on that, right? And you can see up here we have less taper. Same type of service. Here we have none. Now, what they don't show in there, that's definitely got an LSD in it. Okay, when you see a channel that's equal to the tip width of the impeller, you're going to see an LSD in that vein or in that channel. That's just my opinion. I could be wrong, but that's no pinch at all there. But when we get to the top, I want you to look down here. Like this one looks pretty traditional. It comes up and there's no massive area increase. But look this one. So this over here has got this ugly bulb and then this ugly transition. So we dump into a huge area here. You totally lose track of the angle of the gas. Over here, where John was saying, you know, they had a choke issue and they'd have separation. We used to purposely pinch that and then open it up as you go into this vein would create blockage. So from a mathematical perspective, it looked great on paper, right? That the area here with no blockage would equal the area here with blockage. Great on paper, bad in practice. We ruined the range of a lot of those stages. We had more head and efficiency loss in that component. So they're called the ugly diaphragms. And just by changing from ugly to pretty, I don't know, there was no pretty, it would just be go to a better design. But if you got rid of an ugly diaphragm, you could get 3% of mu efficiency on the stage. So if you have an old machine that has that, go to the upgrade group. You don't even have to go to the revamp group where we charge an arm and a lag to, you know, critically think about stuff. You can get performance right there, just on that. I also like using this more like we do today, where we come up and we don't, you know, empty into a volume. This makes me think of the sawtooth diaphragms. I don't have a picture of that. It's another thing that I should add into this is 2B's sawtooth was hideous. It was a terrible way to make a diaphragm, and we've gotten rid of those almost all. And that's all it is. Revamp land is about just making improvements to problems. We do gas mixing totally different today. This was 10 years ago today, but better than originally. Now they'll have a vein that comes all the way down and they'll start to turn the gas before we mix it. So that's like today, you might see a design like that. In a side stream, yeah. In a side stream, they'll bring the vein all the way down into the inlet guide bay portion. Economizer side streams, you can see essentially they're the same, not a real change to how we do that. And then a little bit of a change in how we do the last stage diffuser entrance into the volute, where this kind of opened up that way. And then this was really pointy. You know, we try to make it a little bit more controlled. Okay. Okay, we didn't talk about curves an awful lot. I'll go for another 10 minutes here. We'll try to talk about curves and some of the calculations, okay? So this is how we talk about a compressor. This is the capacity in head again, volume on the bottom, but we don't have head. We have pressure, discharge pressure on the top and efficiency on the bottom. Okay, pressure is kind of like head. So if we look at the polytropic head equation, we have that little R, which is the pressure ratio. Okay. So a head curve and a pressure curve looks a lot the same. If we go back to that curve, I should point out it's variable speed. I take it for granted that you all know that it's variable speed because you see a whole bunch of lines, but those lines are speed. We typically say we got to have a 5% margin to our design. API requires that. And we're going to talk about the components of that curve in another one. I've got to get to that slide. So that's where I'm heading. The the curve, I want to make a really straight point. There's two head equations on this page, and they're there for a reason. The compressor head, mu u squared over g, I mentioned it before, and the polytropic head, okay? So if I look at this curve, this represents what the compressor does, the red and the black. That's the mu u squared over g part. So in this particular gas environment, you can calculate how much discharge pressure is. If you put that in the head, you'd get a head curve, independent of those variables. The gas side of that equation is the dot. So the customer says, I want something that reaches this dot. Sometimes they'll give you 20 dots. Okay. You can only make one compressor. It's made of steel. So if you don't have the movable guide vanes or suction throttle valve or some other means to move that curve, that is the curve. You got the black curve, that was the original. You got the red, that's the revamp. That's not the same machine unless you got drastically different gas conditions. Then you could get that change, right? If you change the mole weight drastically, but this isn't. I know what this curve is because I know it. This is the original, that's the revamp. The customer gave that dot. That dot was this ZRT square root, polynomial, whatever they call this equation with the pressure ratio. If you want to know how much gas horsepower, you take the head, you take the mass flow divided by the efficiency. That's simple. If you're going to talk about flows, customers a lot of times, depending on the service, some give you ACFM, but they usually don't. ACFM is actual cubic feet per minute. And the difference between actual and standard flow is it's at standard conditions, 60 degrees and 14.7 pounds. There's Russian standards. There's all kinds of different standards. So you say standard, but then you have to have what standard are you using? Okay, you'll see that in the data sheets. ACFM, everyone loves, and that's what we plot compressors to. If you're talking about a compressor and you're not seeing it on a volumetric ACFM curve, switch to it. Otherwise, you're not doing it. And I'll show you a curve that looks like that. Okay, mass flow rate. I love that. Mass flow rate is pounds per minute. Okay, that's an important one. If they give it to you in mass, use the mass. If they give you both, sometimes they give you both mass and standard. The only difference is mole weight is in there, right? The standard flow to mass flow. So people say, oh, standard flow is a mass flow. Yeah, it is kind of. When people say standard flow is a volume flow, correct them. Because there's an awful lot of terms between a standard flow and an actual flow. Okay, so volume flow is volume flow. That's an important one. You'll see ICFM for inlet. If you see an I in old terminology, that's A, actual. If you see an S, that's really more like a weight flow. Okay. Coefficient, we don't need that. Okay. An impeller I showed you what a stage is over and over and over. So this is a stage CX curve or a head coefficient and an efficiency coefficient versus a flow coefficient. Flow coefficient is equivalent. Okay. If you have a higher energy gas, it'll get a shorter range. So low mole weights are long curves, high mole weights are short curves. But anything energy related is in there too. Okay. So Smart Perf, we don't do this by hand very often. Smart Perf has these curves that tell you from low to high energy, and it's determining it. And then it interpolates between all those. So you get an interpolated performance based off of an input. So this input, let's say you have 9 stages, it could be in there 9 times, right? And then you're doing a massive amount of math. That's why we don't do this stuff by hand. Okay. This curve could also represent a compressor body. Typically, when you see them this way and you see multiple N over A0 speed lines, that's each line is called an N over A0 speed line. That's the speed it runs versus the sonic velocity, A sub 0. So it's relating it to the gas it's going to be in. When you see it like that and you have multiples, it's usually a stage, an individual stage. Over here, I think I have a better one. I don't want to talk about those terminologies here. Over here is what a typical compressor curve looks like as an output, head and efficiency. But it could be a stage as well. Okay, traditional. Okay, here we go. Stability. So you're going to go from the design point that the customer specified. If there's a whole bunch, you have to pick one in the middle. Okay, they have to tell you. There, in terms of API, there's a point called the rated point. That's usually the highest head and highest capacity point, the farthest on the right or the farthest up. Okay, but if you have a design point, you're going to talk about curved shapes. Now, these are the output curves. This is when you say, I got the whole compressor. You don't typically talk about this on individual stages. You talk about this overall. Stability. is the measure between the design point and when the compressor surges. Okay. You just take that difference and divide it by the design point. So it'd be, let's say if this was 10,000, that's 5,000. You'd go 5,000, 10,000 minus 5,000, 5,000 divided by 10. So your stability would be 50%. Okay. Turn down. Turn down, I don't have a variable speed curve. I have this later, but turn down is the same thing, except stability goes on a constant speed line and turn down goes on a constant pressure or a constant head line. And I've got one of those to show you, but I put the definitions here. Rise of surge is how much head rise you get between the design point and the surge point. API requires us to constantly rise to surge. You have to have a constant rise in head to surge. If this drops over the top, if it starts to droop, you have to cut the curve and it's surged, period. You will see old curves that have that all the way out, especially when you get into movable guide vanes and other things. They drew it way out there, okay? But the API requires you to stop it if the head stops rising. Overload is the other way. It's from the design point out to where we stop drawing the curve. Okay. There's a difference between overload and choke. Overload is where we determine we're going to stop drawing the curve. It could be based on incident angles. It could be based on a relationship between peak efficiency and where you are. Maybe 85% of peak efficiency will stop drawing the curve. 60% of head level will stop drawing the curve because as it starts to droop too much, we just get so far outside of the normal design range that we say we don't have a high confidence in our predicted. So overload, I'm going to take this away. It's important. Overload is where we determine we stop drawing the curve. Okay. Choke is where you can no longer get anything more from the compressor. If you put more work in, you get no more capacity out. That's a choke point. Okay. A lot of people will say, oh, the right side of your curve is choke. Please correct them. That's not choke. Choke is where it really ends, an almost vertical line. Think of it as a vertical line. You put more in, you get nothing out. Then you're choked. Okay. Range ratio is a term they don't often ask about, but we use it to talk about range and when we're comparing compressors. Range is maximum capacity that we draw divided by the minimum capacity we draw. For hydrogen, your range ratio will be 2, 2.2, 2.4 high. If you're in a refrigerant, it's going to be low, 1.3, 1.4. If you're in a really lot of stages in a high mole, you could see it extremely low. High Mach number situations, I've seen it as low as 1.15, and then you're operating on a point. Okay. I have slides that just go through each one of these and they show it. There's the turn down one. I wanted you to visually see that turn down. So surge goes up this line, turn down goes straight across the head or pressure curve until you hit the surge line. Okay. So the surge line is always on a slope. If you see it vertically, it's wrong. If you have a single stage, it's probably more vertical, but if it's truly vertical, it's wrong. Right, John? Okay. It's a big words, but I'm going to say it's always wrong. The surge line, the more sloped it gets, the more stages you have. Okay. So if you have a lot of stages, you'll see this thing tipped right over. If you see a bend in the surge line, that means that one impeller's controlling surge in one area and another impeller is controlling surge. It's not wrong. You can have a kink in the surge line. Okay.
That's where one stage takes over the surge.
Yes.
So stalling to us,
right. Depending that volume reduction term, depending on the volume reduction of the machine, you can have different stages control surge and overload. Okay, so we go through that rotor capacity. I want to do this. Hopefully this clicks. So this is the basic curves. Okay, so this is effects on performance. If you increase mole weight or decrease temperature or increase pressure, that curve will go up. You'll get more pressure rise out of the curve. And it'll increase capacity slightly. Boy, those colors are terrible in this presentation. If you decrease mole weight or increase temperature or decrease suction pressure, that curve will move down and to the left. Okay, and this is a discharge pressure or a head curve. So I like to use a lot of examples, and I have tons of examples in here, and I could talk about each one of them and show you what's going on. We don't have the time to do that because we're running out of time, but this is a suction pressure, a suction throttle effect on an actual compressor for discharge pressure. And you can see on the top left, the blue, the red, and the green are different suction pressures. Okay, you can see that the polytropic head curve is right on top of each other. We didn't change the compressor. That mu u squared over g component is identical, but we changed the conditions that the curve was run at. So you get a change in the discharge pressure, you get a change in the power, and the efficiency is essentially the same. A little bit of a shift there, but if that was drawn all on top of each other, I'd feel a little bit better. This is more about suction throttling if you get this and you want to read through that, but it's showing that API drives us to be having problems in some areas, right? We say API says, well, you have a certain speed margin and you have to have a certain power margin, right? Well, API, they allow us to use suction throttling to determine if we have the right amount of head. And what this is showing is that if you were to use this compressor, you test it, and this compressor tested 6.5% high in head. If you don't use suction throttling to evaluate, you're going to have a 6.5% high in head, and you're going to have a 6% high in power. Okay, fails. But if you use suction throttling to do the same exact condition, you don't run, this is where they wanted it, this is where it ended, right? If you use suction throttling, you move to the right because what happens? The suction pressure goes down, the volume increases. So you make less head. You're out further on the curve, you make less head. You're only 4%, 4.5% high in head, which is within the tolerance. You can be 5% high in head. And you only have a certain amount of power you can be. You're 4.8% high in power. 7 is allowed on fixed speed. So this is, I like this example because it gives you a direct, with the numbers, how suction throttling helps you. It's more efficient to do suction throttling than just fixed speed, like discharge blow off or some other mechanisms, right? This is the other one where I like this curve because this will show you that the polytropic head curve, this is that mu u squared over g, for a lot of different conditions. Each one of these dots has a curve. And you can see the reds, which is all really low flow, and it's in the future had different mole weight. But each one of those colors represents a certain set of performance conditions. And all on top of one another, it's pretty good mix, right? The pressures, the volumes, all these things are changing drastically, but the head versus volumetric stays pretty consistent. When you move that over to a standard volume flow, this thing just breaks apart. That's still head, but it shifts left and right based on the mole weight and the pressures and the temperatures right. If you look at discharge pressure, okay, and you drop it, this is still volumetric flow, but you look at discharge pressure, not head, that pressure ratio curve moves. So this just gives you a visualization of how that is. If you see there, all those points, this is all at the same exact discharge pressure. All of the customer was pushing into a constant pressure header, and they needed that. So all of them are the same discharge, totally different suction pressure. That's why these curves are totally different. Okay. On the head curve, they're the same. And then discharge pressure versus standard volume, I mean, that's just a mess. You can't really even tell. But you can see the groupings of these points are closer when you talk standard volume. So that's why customers typically give you standard volume. That's what they measure. They're measuring a weight flow. Okay. They're not measuring a volume flow. Okay. I got lots of curves in here. Stories between each one of them. But let's see. The last thing, I think this is going to be the last, maybe 2 more slides to go, if you bear with me. Volume reduction is a key component to performance, and that's what makes those curves. If the curve appears to be going away, okay, if you look at any one of these curves, it has a area that's wider than the rest. This one's not too bad. It's pretty consistent left and right, but you can get a hysteresis looking curve. You can get it to shorten up. So if I were to point at it like this at high speeds, you can actually get this to shorten, and it gets like wide here in the middle and then short. You'll get that out of the performance program an awful lot. Okay, this one's it's a single stage impeller. So, or stage, let me see if I can find it multi-stage that shows it. I don't have a lot of them. Even that one doesn't have a lot of turn to it. Here, you can kind of see it in that red. In the red curve, you can see the kink. And so this looks narrower than the middle, and then that looks narrower because this is dropping off. And so that curve shape is called volume reduction is the key to creating a wide operating maps. Okay, I want to teach you this. So inside the compressor, you have 4 impellers, 4 stages. And at a design point, what happens on that first stage is you have an exit pressure, temperature, and therefore volume. So there's an inlet volume, that one we know because it came in the compressor, and then there's an exit volume for that stage. That becomes the inlet for the next stage. So you plot the next stage. It has a lower volume, and you're running at the same speed. So you have this head curve. These 2 curves have a high head profile. These last 2 impellers have a medium head profile, a little bit less head out of those 2 stages. Maybe they're lower diameter. For whatever reason, there's less head coming out of them. But this is the data design point for stage 1, stage 2, stage 3, stage 4. You can see the volume is reducing. So it seems like a common sense term, volume reduction. But the effects of volume reduction is what you struggle to or strive to achieve, is to understand what's going to happen. If you change the flow rate on the left, you can see you still hit on that primary curve. You're entering on the black curve. And if you lower the flow rate, and this curve, unfortunately, lowers it too much. It lowers it almost to the surge point, so you cannot see the effect multiply. You're going to see this on the mole weight better. But as you reduce the flow rate, you're going to make more head with that first curve, which makes the pressure higher, makes the volume of the second stage lower than it would be at design. So even if you move just a little bit off of that point, let's say if you were if you were just here, okay, and let's say that was a 5% shift, on the next stage, you will be not 5% shift in flow. You'll be a 6 or a 7. And then the next one will be 8 or 9. And the next one will be 12, 15, something like that. And you will essentially run out of range faster in a multi-stage selection than you will if you had one stage. Okay, that's the volume reduction effect. So if you increase capacity the same way, and you're here and you go 5% shift, this one shows it really well. This one didn't take this thing is not overloading, right? It's in the middle of its curve still. But its compounding effect, it moved this further out on the curve than it would have. Let's say if this was a 5% shift, this is probably a 6%, 7% shift. Why? Because the first stage made less head, less discharge pressure than it would have at design, higher volume going into the next impeller. It compounds and compounds and compounds, so the last stage hits surge or hits overload faster. Okay. So at high speeds, at low speeds, your curve can come in on itself. You can lose range. Okay. At a single stage, you almost lose no range. But on multi stages, you lose it. Oh, the bottom is mole weight. So I put this on 1. I thought I had 2. The mole weight one shows a little bit better, and that's on the bottom there. Where a very small change to the design point, actually, I think they tried to make that the exact same one, but it's a different mole weight. So the compression is different, and it actually makes an effect on the volume reduction. So you're not in the same area on the last stage as you were on the first. Okay. This is the effects of high volume reduction and low volume reduction. It changes that curve. That's the same impeller or same compressor right there, and 3 different curves based on volume reduction. One is designed for it, and the other ones they're not. The only thing I need you to take away from this is that impellers, the back sweep portion of the vanes, okay, the aerodynamics is going to make a lot of determinations. For us, if you see it's truly radial vane, it's 90 degrees here, you don't see those. They're very high head, lower efficiencies, and a back swept is how you get a little bit better efficiencies out at better range. So you'll see a lot of back swept. This is what that's called. This is a nice curve or a nice slide that Tang put together that shows what happens if you go with more or less vanes, or if you change that angle. It changes the head and the efficiency curve. Now in this, I just want to teach you one more term. The purple curve is the head curve. I can tell that because it doesn't droop as it goes towards surge. The yellow curve is the efficiency curve, and it usually has a peak in the middle. So those 2. What's that other line? That's called the work input. It's simply the mu divided by the efficiency. Okay. The work input line, if you'll see on Tang's, it shows that it can change its slope significantly based on the vane discharge angle. I'm not sure I buy into this, the way Tang set this up. is his calculator. He assumed that the efficiency would stay consistent. If you look at all 5 of those charts, the efficiency is the same. I can tell you that the efficiency for a radial compressor is lower. Efficiency and head are linked. If you alter something that affects the head, you will affect the efficiency and vice versa. Okay. The work input is the health monitor of head and efficiency. So if you have a curve and you look and you plot that work input and it has a kink in it, you got a problem, right? It's usually pretty straight and the slope of it determines a lot of stuff. I don't know if I've ever seen a work input the way he's got it. I've never seen a radial stage. Maybe you have, John, but I don't. Yeah, we just don't use them in our industry. If the work input curve is really that flat, I'd be really, truly amazed. I think the range is hurt and I think the efficiency is hurt. And I put in the notes a little discussion I had with Greg Hoke. I just went to him and I said, "Hey, am I right about this?" And he said, "Yeah, you essentially are." He goes, "But if the efficiency was treated as a fixed, the way it is here, that these principles in those graphs are right." So that's why we put it in there, just so you understand why the impeller has the shape that it does.
Can I add that the work curve is very useful in trying to diagnose a
Performance problems on test.
if the
Yeah.
work curve is where you designed things to be, means your impellers are doing okay.
Right.
And your problem is elsewhere in the station.
Right. In the diffuser return channel, it's somewhere else. Yeah.
Somewhere else.
So what John said is if you calculate your work input and you go to the test stand and your work input slope matches, then your impeller is going to be good. You're looking for a problem somewhere else.
And that's how we found choking at the top of the return channel because the turnaround was not opening up.
Yep. It probably had a big kink in that, right? It started to bend off the work input curve.
No, the work input curve seemed to be okay, at least over the range we tested.
Okay.
It was more that, I mean, our head was dropping off rapidly,
Okay.
and so was the efficiency.
Okay.
We were 10 points short of the design.
Whoa, wow.
Yeah, it was bad.
Okay. One thing we didn't talk about, I'm going to try to do this quickly. I am getting close to the end. Okay. So one of the big components to performance we haven't talked about is the balance pistons. Okay. So I took the slide out purposely, but if you create pressure, there's a pressure differential. There's a high pressure at the end and a low pressure at the beginning. So your compressor has a natural force on those stages that are going to drive it one way or the other, right out of the compressor. You have to balance it. On straight through compressors like this one, we use a component called a balance piston. That's here. The balance piston is rotating. There's a stationary surface and there's a great deal of pressure across it. So you're going to have a high leakage. That leakage rate is high enough to affect the performance of the compressor. We have to get low pressure. Like if you're an IR air blower, they just drill a hole and they come out the side of the compressor with it. I've actually seen that, but it's air, but it's really hot air. So you got to be careful. You don't hurt anybody. Almost all compressors you see, it's not going to be air. It's going to be a gas. And they route it out this dark red and they, come in here at the inlet or here behind the inlet guide vane into this area, or sometimes right into the plenum. Can be there. So in straight through unit, you get balanced back to suction or somewhere. And that leakage could be, I don't know, maybe 1% to maybe 7%, somewhere in that range. Typical is 3. If you don't know anything, just take 3%. So if you're ever wondering how much wasted power you're going to have and you don't know your balance piston leakage, somebody says, "Hey, I'm using this stage and it's this efficient." You're going to do this by hand. Just know that you're going to have loss. So you're going to have 3% additional power just from that. Okay. This is in a compound machine. It's very, very similar, but it adds a couple different areas that it can put in. It can come to the compound return. It can come to the compound discharge or the natural places where straight through. And I will just point out that this has a very unique inlet. This compound inlet is a tangential inlet. It goes around the exterior, it drills, and then this is actually more of a return channel than an inlet plenum. So just in case you see that, you name it, these are snowflakes. Everything has been done. The back-to-back compressor has 2 recycle paths. The one in the middle is what we call a division wall. Okay. People can still call it a balancing drum. That's essentially what it is, or a balance piston. but we call it division wall just so that we know that we're in a back-to-back. That path comes out, no work gets imparted into it. It goes out the diffuser, out the volute. So you have to size those things properly. You have to size your cooler if it goes out and gets cooled and knockout drum and then returns to the compressor. So you have to size all these for that amount of leakage. That amount of leakage can be between 4 and it's 15% of the total leakage. I've seen this to be a massive amount. So it's not something you should overlook. It comes back in and it goes through those 4 stages of compression. So this arrow goes through the back section. The leakage here, because we balance the gas seals or the oil seals or whatever the main process seals are, we balance those. And so we have gas that leaves this and it bounces usually to the other end of the compressor. We almost never do this, although you could do that. If you do that, you're going to have a little bit of a problem with your seal setup. Your seal system has to take that into consideration. So most of the time you're coming to the inlet flange or the plenum or the air of the side UV. They balance the gas seals end to end, and I use the term gas seal now because I'm going to say sometimes they don't. Oil seals, they always balance it, but once we got to gas seals and we realized, hey, we got discharge pressure, we can just leave it unbalanced. We have datum compressors out there. I think other people are doing it where they run at 2 different pressures. It's just a different orifice in the panel line. So you can have it unbalanced. Make sure you know if it's balanced or not when you try to calculate performance. That's really big. That leakage, I've seen it as high as 10, 12%, but because it's at a low diameter and it usually can be at a little bit lower pressure ratio because this is all suction end machine, it can be lower amount of flow. So you could be down in the 2%, maybe 10% max, somewhere in there. But that gas comes out, comes in, it goes through those 4 impellers, comes out the volute, cooled, compressed, cooled, knockout, it comes back in, and it never sees compression in the second section. It goes back there. So this leakage is for the first section, and that leakage is for the second section. It's essentially 2 independent straight through machines if you want to deal with it that way. And if you have a double flow compressor, there's no seals, there's no leakage. Now I have a whole bunch of things on controls, and that was it. My last slide. If we do another one of these courses, we'd get into basic equation worksheets, hand calculators, how you do the stuff on your own. We'd get into smart perf, into Chescui perhaps, and then say, all that stuff that seems really complicated is really, really easy. You put in your 5 components, your pressures, your flow rate, your temperature, your gas conditions, and then it spits it out. You can literally just hunt and peck your way to success, finding an impeller that has the proper loading and all that. The reducing the number of iterations from 1 billion to 5 is the secret of application engineering. I like this place because you can be an idiot and still see success, but it takes a long time to do it until you learn what you're doing. And so that's where the next courses would go, is to show you how to apply some of the knowledge of performance. Sorry, we didn't get into it if that's what you're looking for, but I think now you know you can visualize compressor performance from a practical perspective, because that's what I was hoping for. These are all links, by the way. They will point at the S drive if you get this, so you can go into them. My number's not in there, but reach me in Teams. I'm sure you'll have questions if you get into it, or if you ever want to just be walked through. We don't. You have to learn it with somebody. It's not a self-help course. There's actually that's one thing I wanted to kind of show. See if I can. How do I get out of the presentation mode? Is it going? Okay. So there is some self-help stuff out there if you want it. I can get you the centrifugal basics from IR. That's even lower, you know, the basics before we even get to the compressor. This is what used to be day 1 of AE training. I like it because you can still take it, although it's really, really old. Mother Nature didn't change. So this will walk you through a multi-stage selection and give you the spreadsheet to fill out and it'll walk you through how to calculate all that way. So you can determine how many impellers you need, what size compressor you're going to have, how many stages you need to hit the conditions. This is the handbook. You typically do this on your own, spend 2 days doing this. Then you get a hand calculator. That was in the presentation. That's in Excel. So you get an impression of what it's doing. Then you don't ever have to pick a calculator up again. Then you just use that. Once you get an impression of it in hand calcs, then you go to SmartPerf. And day one of SmartPerf, we can just jump into it. But if you do these two things first, you're really going to be prepared. I would highly recommend it. I give these assignments. I don't know if Luan's still on. I didn't pick on him, but he's a new employee in our group. He's doing upgrades right now. And I said, I gave him those. And you can't do it without asking questions. And that's how I gauge, like, okay, is he ready to do performance yet? He got busy doing other jobs, right? It's like he never asked a question. You can't possibly read. It's 40 pages of really intense stuff. They get into crazy stuff, corrections. They get into gas properties and getting K's and Z's. They actually walk you through how to calculate a K and a Z on your own. Who would ever do that, you know? But yeah, John does. Right. So there is a next step if you want to go further, and then we can certainly, have further classes. We're going to be doing it for Luan, so it's not like you're even putting us out. We're going to train people to be an AE in the upcoming months. So if you want, reach out, join the efforts, and be a performance application engineer. Right? It's great. Peyton, you need training. Okay, anybody online got questions? I appreciate you sticking around till the end.
Thanks, Greg.
Thanks, Greg.
Yeah, hey, Greg, great presentation. Did you say where we could find this document online?
Do we have you have a SharePoint for the stuff you're gonna send out to everybody? Yes.
Right.
She's saying she's gonna issue the email and all the links will be shared. I'm gonna put my presentation right where it belongs. She will make sure. She made sure I recorded, so I'm sure she'll make sure I did it. I'm gonna stop the recording too. Thanks, John.